James Webb has just detected something unusual on the interstellar object, 3IATLAS, something structured, rhythmic, and far outside the chemistry we expect from a natural body. A visitor from beyond our solar system is now producing thermal pulses and patterned light signatures that scientists are double-checking against every known explanation. The closer Atlas gets, the more deliberate its behavior appears, adjusting its trajectory, interacting with Earth's magnetic field, and showing signals that some researchers argue resemble biological or engineered complexity. In this episode, we're looking directly at the measurements, the anomalies, and the hypotheses that are now on the table. If clear, curiosity-driven analysis is your thing, consider liking and subscribing. It genuinely helps these deep dive investigations reach more people. Let's begin. For many years, scientists have used every tool available to study the empty regions between stars. They have tried to measure faint signals, distant heat, and small shifts in light that might show something unusual moving through space. These efforts are careful and slow because most of what the universe gives us is faint and mixed with noise. Missions like Voyager, Hubble, and later the James Webb Space Telescope were built to extend our reach. Each instrument looks deeper and with more precision, allowing us to detect small changes that earlier telescopes would have missed. As our tools improved, so did our expectations, because new sensitivity often brings new questions. Webb, with its large mirror and powerful infrared sensors, was designed to read signals that come from far beyond our solar system. It can detect objects that do not shine brightly, and structures that only reveal themselves through heat or reflected starlight. Its strength comes from its ability to observe wavelengths that pass easily through dust or thin atmospheres. This makes it ideal for tracking dim travelers across the cold background of space. When the telescope performed a routine survey, the mission team noticed a small point of light where earlier scans showed nothing. Faint objects can appear in deep surveys for many reasons, so they checked again. The point was still there, and it was moving. Once additional observations confirmed its path, astronomers realized it was not orbiting the sun like local comets or asteroids do. Its speed and direction showed that it came from far outside our solar system. That made it the third known interstellar object ever detected after the earlier discoveries of Oumuamua and Borisov. These objects are important because they carry material that formed around other stars. Studying them gives us a chance to compare our solar system with distant ones. Most interstellar objects pass quickly and quietly, leaving only small clues about their origin. They are often cold, dim, and difficult to track. For that reason, finding one early is rare and valuable. The new object was labeled 3IATLAS, written as 3I/Atlas, but read as 3IATLAS. At first, it seemed similar to other interstellar visitors. It appeared to reflect sunlight, and its brightness changed in a way that suggested a rough surface. But as Webb gathered more data, the readings became unusual. Many comets brighten as they warm, but their glow is uneven. They release gas and dust when pockets of ice turn into vapor, and this process happens in unpredictable bursts. 3IATLAS did not behave like this. Its infrared signature showed a steady rhythm of heat flowing outward, as if a small, warm region inside was turning on and off in a controlled pattern. This type of pulse did not match the behavior of ordinary rocks, and it did not match the heat patterns of comets that warm as they approached the sunday. To understand this better, it helps to know how an infrared telescope measures heat. Space objects absorb sunlight and then release energy slowly as they cool. The patterns of this release help scientists estimate the surface properties. A scattered or uneven pattern usually means a natural surface with areas of ice, dust, or rock. But in this case, the telescope saw a narrow region of heat centered deep within the object. The energy came out in timed intervals, with each interval nearly identical to the one before it. The pulse did not depend on the object's distance from the sunday. It did not change when the viewing angle shifted. These details led researchers to wonder whether the source of the heat was internal rather than simply reflected or absorbed sunlight. As teams at NASA and the European Space Science Agency reviewed the data, they compared the thermal pattern with known types of natural pulses. Some pulsars, neutron stars, and quasars release energy in steady cycles, but they operate on scales far larger than a small object moving through our solar system. Their timing, wavelength, and intensity follow patterns tied to their mass, rotation speed, and magnetic fields. Nothing about 3IATLAS matched those profiles. The object was far too small to behave like a compact star, and the energy it emitted was too limited to suggest a large internal source like radioactive decay. The pulse appeared weak but steady, and its regularity made it difficult to ignore. Then researchers added another layer of data, the spectrum of the light coming from the object. When the telescope studies light, it separates it into different wavelengths, creating a pattern similar to a barcode. Natural light reflects off rough surfaces and spreads out across a wide range of wavelengths. But some types of light focus into narrow bands, which is unusual for natural objects. These narrow bands often appear when energy is guided or controlled, similar to how certain wavelengths are used in communication technology. When the team compared the spectrum to known natural sources, no close matches were found. The readings showed energy concentrated into focused wavelengths rather than scattered across the spectrum. Because the signals were faint, data scientists applied a method called a Fourier transform to analyze the pattern. A Fourier transform breaks a signal into smaller repeating parts to reveal hidden rhythms. This is useful when noise hides structure or when signals mix with background interference. When the team used this method, they found ordered intervals inside the thermal pulse data. The intervals repeated with high precision, forming a sequence that did not shift over time. Natural objects can show repeating behavior, but there are limits to how consistent those patterns can be. Processes like sublimation, rotation, or impacts tend to vary as conditions change. Heat pulses caused by melting ice, for example, rise and fall as the surface reshapes itself. But 3IATLAS did not show those variations. Its pulses were nearly identical, even when the telescope observed it on different days. Some researchers suggested the pattern might still come from an unknown natural process. Space holds many phenomena that do not fit our current models, and interstellar objects may carry materials or structures we have not studied closely. Others pointed out that the pattern resembled telemetry, which is the steady transmission of measurements from one place to another. Telemetry on Earth can come from satellites or probes, which often send narrowband signals so that receivers can separate them from noise. The similarity raised questions, but the teams remained careful. Without a clear source or evidence of intent, they avoided conclusions that could not be supported by measurable data. What complicated the discussion was the consistency of the pulses. Observations taken over several weeks showed the same interval. The strength of the signal did not fade or spike. The timing did not drift, even when the object moved into regions with slightly different solar radiation. The thermal rhythm stayed the same. This stability is not typical for natural bodies. Most objects warm or cool depending on sunlight, rotation, or surface changes. Comets, for example, often become more active as they approach the sun, releasing gas and dust in bursts. Asteroids can change brightness as they spin, but 3IATLAS kept the same repeating pattern, which gave analysts more data points to compare. As the research continued, the teams looked for alternative explanations. Some examined whether the pulse could result from internal stress or cracks releasing heat in a steady cycle. Others checked whether distant reflections or sensor artifacts could create false pulses. Each test removed one possibility. The more the data was cross-checked, the more the pattern held. Scientists reviewed older records to see if similar objects had passed close enough to measure, but the previous interstellar visitors behaved differently. Oumuamua did not show steady heat, and Borisov acted like a typical comet, releasing gas and dust as expected. Because the light spectrum appeared focused rather than scattered, analysts studied its wavelengths with more detail. They found narrow peaks that aligned with specific bands often used in scientific instruments. These wavelengths are not exclusive to artificial sources, but they are rare in natural settings. Some minerals can produce faint narrowband emissions when heated, but their signatures vary with temperature. 3IATLAS did not show those variations. The peaks stayed fixed, separated by consistent gaps, and appeared each time the telescope observed the object in the same measurement mode. This led to deeper analysis of the internal rhythm. When the pulses were plotted on a timeline, the intervals formed a clean sequence without random drift. If a natural process caused it, it would have to be something not yet observed in comets or asteroids. No known physical mechanism inside small icy bodies can maintain such even timing over a long period. Internal processes like cracking, heating, or gas pockets normally create noise, not order. But in this case, the order remained. As the investigation expanded, some groups suggested the object might be releasing stored heat through a controlled but natural mechanism, perhaps from layered materials that melted or re-solidified at predictable thresholds. Yet this idea required materials with properties not yet seen in interstellar objects. Others considered whether the pulse could be linked to magnetic effects, but the wavelengths did not support that explanation. A few researchers proposed that if the object carried complex chemistry from another star system, the reactions inside it might behave in unfamiliar ways. This possibility kept the discussion open but did not match the stability of the pulse. The more the team studied the data, the more they returned to the original observation. The pattern inside the signal did not drift. It did not change course. It did not become weaker or stronger. It did not react to outside forces in the way natural objects typically do. The pulse never changed. From the moment the James Webb Space Telescope first detected the steady pulse inside 3IATLAS, the signal remained unchanged. It stayed constant through changes in sunlight, distance, and background radiation. For researchers, this level of stability was unusual. Signals from natural objects almost always vary. A comet's brightness shifts as it warms. An asteroid's reflected light changes as it rotates. Even distant pulsars, which are known for their regular timing, show small drifts over long periods. But the signal from 3IATLAS stayed fixed, without any measurable shift in pattern or strength. This consistency gave scientists confidence that the readings were not sensor noise. Yet it also raised questions, because natural processes rarely behave with such exact repetition. The team reviewing the data considered how different factors might influence the pulse. They looked at solar radiation, the angle of observation, and the object's rotation. None of these appeared to affect the signal. The thermal pulse repeated on the same schedule, with the same energy for every measurement. Researchers compared it with other known sources of repeating signals. Pulsars, for example, create highly regular electromagnetic pulses as they spin, but they also release energy across large regions and at frequencies far beyond what a small object could generate. The pulse from 3IATLAS was faint, steady, and localized. It did not resemble the natural rhythms tied to massive stars or compact remnants. As scientists tried to fit the data into known categories, a new event forced them to reconsider their assumptions. Without any warning, the brightness of 3IATLAS rose sharply. Instruments recorded an increase of about 40% in less than 2 minutes. This rapid flare drew attention because natural objects rarely brighten so smoothly or so quickly. Comets sometimes have sudden outbursts when pockets of ice vaporize, but these events are messy. They produce irregular spikes in brightness and unpredictable clouds of dust. The flare from 3IATLAS, however, rose in a clean, even curve. It did not show the noise or scatter that accompanies natural outgassing. It appeared as though the entire surface brightened at once. Alongside the brightness increase, the infrared sensors detected a uniform rise in temperature. The heat did not begin in one part of the surface and spread outward. Instead, the whole object warmed nearly at the same moment, as if a source inside had changed its output. For researchers, this suggested a type of controlled release rather than a random thermal surge. Natural heating from sunlight affects surfaces unevenly, and internal heating from chemical reactions typically begins in specific regions. A complete, synchronized rise in temperature did not match the expected behavior of a comet, asteroid, or frozen interstellar fragment. The next change came from the object's movement. Before the flare, its trajectory followed a predictable path shaped by gravity. The object moved through space in a way consistent with its speed and distance from the Sunday. But after the thermal surge, its course shifted. The change was small at first, measured in tiny fractions of 1 degree. These shifts, while subtle, mattered because astronomers track such objects with extreme precision. Even small deviations stand out when compared with orbital predictions. Over the next series of observations, the shift became clearer. 3IATLAS was no longer drifting along a passive arc. Its path corrected slightly, then corrected again. It moved in a way that appeared guided by an internal adjustment rather than external forces. Instead of heading directly toward Earth, the new trajectory aligned with the inner region of the solar system. The curve placed the object just inside Earth's orbital path. This alignment required accuracy, because even a small miscalculation would place it far from the predicted position. Natural bodies do not make such clean directional changes on their own. Gravity from nearby planets can alter a path, but only with long, sweeping arcs, not precise and incremental adjustments. The new course prompted more detailed modeling, and the data kept pointing to the same conclusion. The movement did not match the pattern of a passive object drifting through the solar system. After confirming the trajectory shift, the European Southern Observatory reviewed the spectral data again. They used algorithms normally applied to the study of exoplanet atmospheres. These tools separate light into its components to detect organic molecules or gases. When they filtered the emissions from 3IATLAS with this method, the results were unexpected. Inside the spectrum were small, repeating fluctuations. These fluctuations mirrored the types of frequency shifts seen in biological systems. They were not signs of DNA or proteins. Instead, the changes occurred at resonance levels similar to the oscillations found in living cells. On Earth, many biological processes create patterns of energy that rise and fall at regular rates. The data from 3IATLAS showed a similar type of rhythmic change. Researchers approached this carefully. Patterns resembling biological rhythms do not automatically indicate life. Some chemical systems show regular oscillations when energy flows across different layers of material. Certain crystals also shift energy in repeating cycles when exposed to heat, but the frequencies detected in the object did not match known chemical or mineral processes. They followed timing intervals that fit more closely with the movements of living membranes or cellular structures. The signals did not prove that the object was alive, but they did suggest that something inside it behaved in a way commonly seen in biological environments. If the object contained material that acted like living tissue, scientists considered two possibilities. One was that the object itself was partly biological, similar to a structure built from organic systems. The other was that it carried biological matter inside it, perhaps protected by layers that shielded it from space. Both possibilities required careful review because no confirmed biological system has ever been found surviving the conditions of interstellar space. Even strong microbial life from Earth would face extreme radiation, freezing temperatures, and collisions with dust particles over long distances. For biological structures to persist, they would need protection or processes unlike anything observed locally. Just as scientists began exploring this idea, the readings changed again. The energy output dropped sharply. The thermal pulse flattened into a steady, low level. The narrowband emissions faded. The biological-like fluctuations weakened until they became almost imperceptible. Yet the object's movement did not slow. It did not drift off course. It continued along the corrected trajectory with the same precision as before. This combination, a drop in measurable activity while maintaining controlled movement, added another layer of complexity. Some researchers compared the shift to a low-power mode, similar to how spacecraft reduce energy output while keeping essential systems active. Natural objects do not typically behave this way. When a comet loses thermal activity, it generally becomes less stable. Its outgassing slows. The rotation may change, and the path can drift. But 3IATLAS held its course. Observers noted that the reduction in energy was smooth and controlled rather than chaotic. The transition suggested that whatever process drove the earlier pulses was not a simple reaction to sunlight or temperature. It appeared to adjust intentionally, or at least systematically. As teams reviewed the data, they discussed whether the object might have responded to its environment. They considered whether the flare and the later drop in emissions were part of a cycle. Some wondered if the earlier brightening signaled a transition between internal states, like a preparation step followed by stabilization. A few researchers raised a different question: whether the change in activity occurred because the object detected something in its surroundings. These ideas remained speculative, but the pattern of behavior, first active, then quiet but controlled, raised new questions about how the object regulated its energy. Attention then turned closer to Earth. A network of instruments continually monitors the planet's magnetic field. Among these regions, the South Atlantic anomaly stands out because Earth's magnetic protection is weakest there. Satellites often experience increased interference when passing through it. During the period after 3IATLAS adjusted its trajectory, sensors in this region detected small electromagnetic ripples. These ripples did not match patterns from solar flares or gamma-ray bursts. Instead, their timing aligned with the trajectory shifts recorded from the object. The measurements were faint but consistent. Researchers cross-checked the pulses with data from other monitoring stations. They wanted to rule out electrical noise, equipment errors, or natural fluctuations in the magnetosphere. After filtering the information, the signals still matched. They occurred at intervals synchronized with the object's movement through the outer layers of the heliosphere. Earth's magnetic field responded in ways not previously documented. No comet, asteroid, or interstellar fragment has ever produced a measurable effect on the magnetosphere from such a distance. Known natural bodies do not generate electromagnetic fields that sync with Earth's systems in this manner. Physicists examined the possibility of indirect interactions. For example, charged particles emitted by solar winds sometimes create disturbances, but in this case, there were no changes in solar activity that could explain the ripples. The pulses did not match space weather patterns. They appeared to form a link between the object's movements and subtle reactions in Earth's magnetic envelope. The signals were weak but precise, leaving researchers without a clear natural mechanism to explain the synchronized electromagnetic responses. From the observations gathered so far, scientists began to consider whether the object's emissions were interacting with Earth in a measurable way. The earlier synchronized pulses in Earth's magnetic field had already suggested some form of coupling, even if the mechanism behind it was still unknown. In physics, when two distant systems show responses at matching intervals, researchers usually look for a shared influence or an underlying link in their environments. In this case, the timing aligned too closely to be dismissed as coincidence. While no one could conclude that the object was sending information by design, the idea that both systems were interacting through a physical or energetic pathway could not be ignored. The main takeaway at this stage was that the signals from 3IATLAS were not isolated. They appeared to coincide with changes detected within Earth's magnetic envelope, creating a basis for further investigation. As data continued to accumulate, a group of independent researchers brought forward a theory that sat outside the boundaries of mainstream models. This group did not present their work as fact. They instead framed it as a hypothesis that might explain the unusual patterns in the thermal pulses, the narrow band emissions, and the synchronized magnetic responses. Their suggestion was that 3IATLAS could be more than a simple interstellar rock or a fragment from another star system. They speculated that it might represent a form of intelligence that developed through processes not observed on Earth. This idea was not positioned as a replacement for established science, but as a possible interpretation when conventional explanations no longer fit the measurements. To make their case clearer, they described how intelligence is usually defined through biological structures built from carbon-based molecules and neurons. On Earth, cells store information chemically, and tissues coordinate behavior through electrical and chemical signals. But the group noted that life elsewhere may not follow the same design. In environments with extreme radiation or thin plasma fields, different pathways for complex organization might exist. They considered the possibility that self-regulating systems could arise from patterns in electromagnetic fields, charged particles, or engineered materials that stabilize under specific conditions. If such systems could maintain structure, respond to stimuli, and preserve information, they might operate in ways that resemble intelligence without relying on familiar biological chemistry. The idea extended further by proposing that 3IATLAS might be an entity formed over long periods through interactions in interstellar environments. Instead of being built in a laboratory or piloted by another species, it could be the outcome of natural processes that allow matter and energy to organize themselves in complex ways. In this view, intelligence would not require a nervous system. It would instead emerge from stable patterns that adapt over time. Plasma filaments, magnetic loops, or engineered matter could provide the framework for behavior that appears directed. These ideas remained hypothetical, but they were used to explore why the object's signal stayed consistent and why its trajectory changed in precise steps without known external forces. The researchers emphasized that if such systems existed elsewhere, they might evolve in environments where carbon-based life could not survive. They discussed how electromagnetic structures can form coherent shapes across large distances and how certain materials might hold stable patterns under extreme conditions in deep space, where radiation, vacuum, and temperature challenge traditional life. A different form of adaptation might take place. Under this interpretation, intelligence could form in environments that Earth-based models are not designed to describe. It would not contradict physics. It would simply expand the range of possibilities. From this line of reasoning, the group presented another idea to frame the object's presence. They suggested that if such a system were capable of long-term stability, it might travel across star systems, not with a mission, but as part of its natural behavior. Rather than being a visitor arriving with intent, it could function as a traveling structure, responding to conditions as it moves. If it interacted with civilizations that reached a certain level of observation, its signals might finally be detectable. In this scenario, its presence near Earth would not be an act of arrival. It would instead be a moment when our instruments became sensitive enough to register it. While these ideas were discussed in limited circles, astronomers continued to track the object with more precision. Observatories around the world recalibrated their equipment to follow the object closely. As the data improved, a new measurement raised further questions. The region of space around 3IATLAS showed patterns consistent with gravitational lensing. Gravitational lensing occurs when a massive object curves the path of light around it. This effect is usually associated with extremely dense bodies such as galaxies or black holes. For an object smaller than a moon to create noticeable curvature was unexpected. Scientists estimated the object's mass based on its movement and the gravitational influences acting on it. The lensing patterns did not match the expected values. They suggested either more mass than the object's apparent size could support, or a form of gravity manipulation that was not accounted for in the models. When comparing these measurements to predictions, astrophysicists found discrepancies that their current equations could not reconcile. Even when factoring in uncertainties, the difference remained too large to dismiss. Researchers considered whether the object contained dense materials that were not detectable on the surface. They also evaluated whether a cluster of smaller fragments might surround it, creating a combined effect. Neither explanation aligned with the data. The curvature appeared to come from a compact region, not a distributed cluster. Some theorists proposed that the object could be adjusting local gravity fields in controlled ways. They did not claim that gravity was being created or destroyed. Instead, they explored whether existing gravitational effects could be shaped or redirected. This would allow an object to navigate with minimal energy while maintaining smooth and precise motion, similar to how a vehicle adjusts its buoyancy in fluid to move quietly. While this idea remained speculative, it offered a framework for understanding why the object changed course so gently and without known propulsion. If it could influence gravitational gradients around itself, small adjustments would allow it to shift its trajectory by fractions of 1 degree at a time. In the models tested, very little energy would be required for such corrections. The process would differ from engines or thrusters. It would rely on the fundamental forces already present in space. As the gravitational data continued to be studied, another event drew the attention of multiple research teams. A small object trailing behind 3IATLAS separated from it and moved independently. At first, this was classified as debris. Comets often shed fragments when internal stresses or temperature changes break pieces from their outer layers. But when the James Webb Space Telescope examined the fragment more closely, its shape did not match natural debris. Instead of being rough or irregular, the fragment appeared to have smooth surfaces, edges met at right angles, and the faces aligned symmetrically. Geometric shapes with straight lines and perfect corners are rare in natural objects. They usually require controlled conditions to form. Researchers studied the light reflected from the surfaces and found patterns consistent with intentional shaping. The fragment did not show the chaotic scattering typical of rock or ice. Instead, it reflected light in a uniform way, suggesting a consistent structure across its surfaces. This raised the possibility that the fragment was part of a larger framework or internal component that had broken free. The next discovery came from analyzing the fragment's thermal signature. Natural objects almost always emit some form of heat, even if extremely faint. They absorb energy from sunlight or store internal heat from chemical reactions. But this fragment emitted no detectable temperature at all. Infrared sensors registered nothing beyond background space levels. It did not warm under sunlight, nor did it release heat as it cooled. This behavior suggested a material with unusually low emissivity, or a composition designed to block or absorb energy with high efficiency. When scientists examined its composition using spectroscopy, they detected atomic signatures not matching any known alloys on Earth or in meteorite samples. The material appeared stable under radiation and did not break down or erode. It absorbed incoming light and released no measurable output. These properties were unusual even among engineered materials. The fragment did not show signs of decay, heat, or chemical reaction. Its structure remained uniform in every observation. Observatories tracking the main object then turned their attention to its rotation. Many elongated objects spin as they travel due to uneven impacts or inherited angular momentum. But the rotation of 3IATLAS showed a pattern that did not match random tumbling. Instead, the object rotated in intervals that appeared tied to consistent mathematical relationships. When researchers plotted the angles and timing of its spin, they found ratios close to the value of pi, expressed as 3.14. They also found proportions similar to the golden ratio, approximately 1.618, and sequences aligned with prime numbers. Mathematical constants appear in many natural systems, but the combination and repetition observed here raised questions. Researchers examined whether these values could arise from internal structure or mass distribution. They tested whether the spin might stabilize around certain harmonic frequencies. While some natural explanations remained possible, the alignment with specific constants drew attention because of the precision involved. The intervals repeated with minimal drift, echoing the stability seen in the object's thermal pulses and trajectory changes. Some scientists considered whether the rotation could serve as a form of expression. Instead of sending signals through radio or light, the object might encode patterns in its motion. Motion-based communication is not common in astronomy, but rotational signaling has been discussed in theoretical models. In these models, the spin of an object conveys information through timing or alignment. If 3IATLAS were using such a method, the rotation would need to be consistent and observable. The object's stable spin made this plausible, at least as a hypothesis to examine. As the teams compared all these findings, they returned to a central question. The object's behavior included stable pulses, controlled changes in movement, unusual gravity interactions, and geometric debris. None of these phenomena alone would suggest a clear purpose, but together, they created a pattern that did not fully match natural bodies. Whether the rotation communicated something intentionally or simply reflected internal processes remained uncertain. Observers noted that the rotational cycle repeated without drifting, as though it was calibrated rather than left to random forces. This brought researchers to a point where they had to consider how the observations fit together. Each measurement could still have natural explanations, but the combination encouraged further study. If the rotational timing carried meaning, it might be intended to be recognized by anyone watching closely. If it was not intended, then it still represented a structured process that reflected an organized internal state. In either case, the rotations appeared to present a pattern visible to observers capable of measuring them. At this stage, the data raised a final question that remained unanswered. The spin formed consistent intervals, aligned with known constants, and repeated with precision. Whether these movements were deliberate or simply a product of internal mechanics was still unknown. Researchers continued tracking the rotation to determine whether the pattern would shift as the object traveled deeper into the inner solar system. For now, the behavior stood as a repeating cycle, a message designed to be seen, not heard. And it raises the ultimate question: are we witnesses or the intended recipients? As scientists continued to examine the unusual behavior of 3IATLAS, they pushed their instruments to gather every possible form of measurement. After the geometric fragment, the gravitational anomalies, and the rotational patterns. A final set of readings brought attention back to the material trailing behind the object. These samples had already shown unusual signs, but researchers wanted to know whether anything inside the faint dust and debris behaved like components of life. To check this, they applied a set of detection algorithms designed to identify chemical patterns that often appear in early biological processes. These algorithms do not search for complete cells or complex organisms. Instead, they look for repeating molecular signatures, unstable chains, or sequences that shift in ways consistent with simple replication. When the data was processed through this system, the output revealed faint but distinct organic signals. They were not stable carbon structures or remnants of proteins, which would have suggested long-dead biology. Instead, they appeared as flickering patterns, rising and falling in a way that suggested movement or change inside the molecules themselves. This type of signal sometimes appears in environments where simple compounds assemble themselves into temporary structures. Scientists often call these precursor systems because they show behaviors that resemble early steps toward replication without becoming true living forms. The signals in the tail of the object fell into this category. They were irregular, yet repeated often enough to show that they were not random noise. This discovery led researchers to consider two main explanations. The first was that the material might be a kind of camouflage. In biology, many species produce patterns or shapes that help them blend into their surroundings. On Earth, some animals shift their colors, match textures, or imitate other organisms to avoid predators. Even viruses use chemical mimicry, forming structures that resemble proteins to pass through defensive barriers. If 3IATLAS had internal systems made from engineered materials, it was possible that the organic-like signals scattered along its tail could make it appear more natural. Sensors designed to track comets and asteroids often look for common organic compounds, so adding such signals could cause observers to underestimate its complexity. The second explanation involved a more expansive idea. Some scientists propose that life in the universe may spread from one place to another through a process known as Panspermia. This concept suggests that biological material can move across large distances, carried by rocks, dust, or artificial probes. Natural panspermia would rely on impacts or chance events, while directed panspermia involves the intentional spreading of biological components. In this context, the organic signatures trailing behind 3IATLAS could represent a form of distribution. Instead of hiding its presence, the object might be carrying material that can seed biological systems in suitable environments. These structures would not be full organisms. They would be simple building blocks, waiting for the right conditions to develop further. While these ideas were being studied, another set of measurements began to attract attention. Multiple magnetometers, located both on Earth and on spacecraft throughout the solar system, detected rhythmic shifts in the magnetic fields around them. Magnetometers measure changes in magnetic intensity, and they often record signals from solar storms or variations in the solar wind. Those natural events usually produce chaotic patterns with no strict timing. The new signals, however, did not resemble turbulence or random interference. They appeared in triplets, spaced evenly, like a repeating rhythm. The pattern was unusual because it did not weaken as the distance between the object and the magnetometers increased. Instead, the amplitude of the pulses grew stronger, as 3IATLAS moved closer toward the inner part of the solar system. This suggested that the object was not simply producing magnetic energy that spread outward. It seemed to be interacting with the magnetic fields inside the solar system itself. Each pulse showed up in the same sequence, recorded at nearly the same time across different instruments. The idea that the object might be mapping, responding to, or synchronizing with the magnetic layout became a serious consideration. Researchers compared the triplet pattern to known magnetic behaviors. Planetary fields can sometimes create repeating signals, but only when driven by internal rotation or strong solar wind interactions. None of those conditions matched the observed timing. Solar storms vary wildly, and planetary magnetic responses are not synchronized in triplets. The signals here were too consistent and too coordinated across different detectors. This consistency led analysts to explore whether the pattern could reflect a scanning process. A scan would require a system to probe its surroundings and adjust the output based on feedback, resulting in a controlled sequence. Though this remained hypothetical, the measurements fit that interpretation more closely than any natural pattern observed before. As the data became more compelling, communication specialists decided to send a controlled signal toward the object's last known position. They used antennas from the Deep Space Network, which are capable of transmitting precise radio pulses across long distances. The signal they generated was built from simple and universal patterns, such as prime numbers, binary sequences, and evenly spaced tones. The idea behind these patterns is that they are not tied to any single culture, biology, or language. They are mathematical, stable, and recognizable by any system capable of analyzing numbers or timing. After the transmission was sent, the team waited for a return signal or any disturbance that might show an interaction. No radio echo arrived. There was no shift in the background noise or spectrum. At first, it seemed as though the object had not noticed or had chosen not to respond. But about 1 hour after the final broadcast, astronomers detected a slight change in the object's rotation. The shift was small, too small for most instruments to detect. Only the group that had been studying the detailed spin behavior could measure the difference. The timing was close enough to raise questions, but not enough to draw conclusions. In fields that study decision-making or communication, a pattern like this is sometimes called deliberate non-response. It means that an entity is aware of a contact attempt but does not choose to reply. Scientists did not say that this was the case with 3IATLAS. Instead, they noted that the rotation shift and the timing of the broadcast overlapped in a way that made the connection worth examining. The response, or lack of response, did not match the behavior of a natural object simply absorbing energy or ignoring a signal. It resembled a system that registered the contact and changed one of its parameters for reasons that were not understood. As investigations continued, another discovery emerged from a review of older data. Infrared sky surveys and deep space catalogs contain decades of observations that record background heat and faint objects. When researchers examined surveys from the years 1987, 1998, and 2013, they found small anomalies along the same path that 3IATLAS currently traveled. These anomalies were faint disturbances that had been marked as noise or instrument artifacts at the time, but when compared with the new trajectory, they lined up with surprising accuracy. Each anomaly appeared during a period when other unusual events were recorded. In 1987, several observatories detected unexplained bursts of radio energy. In 1998, gravitational wave detectors registered fluctuations that did not match known astrophysical events. In 2013, similar small anomalies occurred, again without clear sources. When all the data points were combined, a pattern began to form. It suggested that the object might have crossed near our system before, leaving brief traces that went unnoticed until now, because instruments were not sensitive enough to see the underlying structure. If this interpretation was correct, then the current encounter might not be the first. The object could be following a looping path through space that brings it near our solar system at long intervals. A looping path would not require circular motion. It could be a long, stretched orbit, or a trajectory shaped by gravitational interactions over time. If it had passed by before, it might have observed changes in planetary systems, including Earth. This possibility raised new questions about the nature of the object's movement and its purpose. The earlier traces would not necessarily mean intent or repeated visits, only that its path intersects our region more than once. Scientists approached this information with caution. Many natural objects follow long, complex paths shaped by distant gravitational forces. A looping trajectory could occur without any guiding influence, but the alignment of anomalies with the object's current direction encouraged researchers to study whether the pattern signaled something more than coincidence. If the object had been present near the solar system in the past, then its return suggested a repeating cycle. And if the cycle lined up with periods of increased activity in radio signals and gravitational disturbances, those coincidences needed to be understood carefully. Putting all the observations together, researchers now faced a scenario in which 3IATLAS might not be passing through the solar system for the first time. It could have approached before, moved away, and returned along a path shaped by factors still unknown. If that was the case, then the object was not a brief visitor moving through space one time. Instead, it might be part of an ongoing pattern, appearing at intervals that connect with changes in the local environment. The idea did not confirm any single explanation, but it expanded the range of questions that scientists needed to consider. At this point, the evidence suggested that the object's behavior was not limited to the present moment. Its earlier traces, combined with new readings, pointed to the possibility of a presence that repeated over long periods. Researchers still did not know what drove the object's path, or why its signatures matched past anomalies. They only knew that the data formed a pattern that warranted further study. If 3IATLAS truly followed a long, looping route that brought it near our system more than once, then this encounter was part of a larger cycle. And if that is true, this is not just an object passing by. It is a repeating presence, possibly observing cycles of planetary development, human progress, or maybe something much deeper encoded in Earth's own timeline. As researchers continued refining the models for 3IATLAS, new calculations began to show details that earlier versions had missed. With more data points and better measurements of the object's velocity and position, teams could update its predicted path with higher accuracy. These recalculations revealed that the object was not steering toward Earth or moving into a direct solar encounter. Instead, its trajectory curved in a way that brought it near one of the most studied moons in the outer solar system, Europa. Europa orbits Jupiter, and has long been considered one of the most promising environments for life. Beneath its icy shell lies a deep ocean warmed by tidal forces, creating a setting where chemical energy and liquid water may interact. When scientists looked beyond this close pass, they noticed something else. If 3IATLAS continued on its path and later performed another arc through the system, its extended route could intersect with a second ocean world, Enceladus, one of Saturn's moons. Enceladus also contains a subsurface ocean, and previous missions detected plumes in which water vapor, organic molecules, and small grains escaped through cracks near its south pole. Both Europa and Enceladus are frequent targets in discussions about where life might exist beyond Earth. Because of this, the new trajectory of the object gained attention from teams studying planetary habitability. The alignment did not prove intent, but it showed a pattern worth examining. This raised a broader question. The earlier focus on Earth came from the assumption that the object's behavior was related to human presence or activity. But if the trajectory favored passes near icy moons, then Earth might not be the central point of interest. Instead, the object might be moving along a route shaped by the natural layout of the solar system's most life-relevant environments. Researchers examined whether the arc provided opportunities for scanning, measuring, or observing regions where prebiotic or biological chemistry might develop. Scientists studying the outer planets noted that Europa and Enceladus both present conditions that support chemical gradients. Warm vents on the ocean floors could create environments similar to places on Earth, where early life is thought to have emerged. If a system designed for long-term observation passed through the solar system more than once, returning at intervals shaped by gravitational paths, it could gather information about how these environments change over time. This interpretation did not assume purpose or intelligence, but it reflected the scientific interest these moons already hold. As the object moved farther into the inner solar system, signals from deep space probes began to fade into weaker layers of static. Even so, the magnetometers on several spacecraft and ground-based stations continued to pick up rhythmic magnetic changes. These measurements showed steady triplets, a repeating pulse that did not match known sources of magnetic fluctuation. Over time, the amplitude of these pulses increased. This pattern suggested a form of interaction, where the object might be responding to the magnetic structure of the solar system or taking measurements based on it. Engineers who study spacecraft behavior compared these patterns with how some instruments collect data. In many missions, probes switch into low-emission modes when they need to gather precise measurements or conserve energy. In these modes, the probe limits outgoing signals and focuses on receiving information. If 3IATLAS behaved similarly, then its lack of communication could reflect a state where its systems were designed to observe rather than transmit. This interpretation focused on how the object gathered information, not on why. Even with this cautious framing, some researchers proposed that the silence might not indicate damage or malfunction. Instead, it could reflect an operational mode meant to limit interference or interaction. A system that aims to measure electromagnetic fields across wide regions would not need to broadcast. It would simply detect changes and record them. The observed behavior could be consistent with this type of passive operation. This idea did not confirm intent. It only suggested a possible explanation for the data. As teams examined the magnetic signals, they also considered the possibility that the object might have methods for gathering information without sending detectable emissions. The idea was that the object could be scanning the solar system's magnetic layout in a structured way. Patterns in the data supported this possibility, but the absence of clear communication meant that there was no way to verify it directly. While these discussions continued, another analysis took shape. A research group at the California Institute of Technology examined the organic spectral data collected earlier. Instead of comparing the signals to hypothetical extraterrestrial sequences, they analyzed them against Earth-based genomic markers. They used a model that searched for patterns in repeating molecular sequences, structural motifs, and arrangements commonly found in genetic or pre-genetic material. The results showed parallels. These parallels were not direct matches and did not indicate a shared origin. Instead, they revealed that certain repeating structures in the object's organic residue resembled patterns seen in Earth's simplest biological components. Some of the signals aligned with motifs found in viruses, small repeating segments often present in retrotransposons, and segments of non-coding DNA. Non-coding DNA does not build proteins, but it contains patterns shaped by chemistry and evolution. Because these structures are common across many forms of life on Earth, similarities in the signals did not necessarily point to a connection. They could reflect basic chemical rules that guide how molecules organize themselves into repeating units. Scientists at the Institute emphasized that these patterns did not prove the presence of genetic material. Instead, they indicated that the residue contained structures that could behave in ways familiar to early biochemical systems. If these structures were capable of adapting in different environments, they might represent universal templates for chemical organization. In other words, they could be building blocks that form under a wide range of conditions, driven by chemistry, radiation, and environmental energy, rather than by any specific biological history. From this perspective, the material trailing 3IATLAS could hold sequences shaped by universal processes. These sequences might be able to integrate into new environments by adopting different forms depending on temperature, pressure, and available elements. The researchers did not claim that these structures seeded life on Earth. They simply noted that the patterns had similarities to molecular arrangements found in Earth's early biological systems. These similarities could arise naturally in many places where chemistry follows certain energetic paths. As the scientific community debated these findings, the overall narrative of the object's behavior shifted. Instead of focusing on communication attempts or dramatic interpretations, researchers began organizing the observations into categories: trajectory, magnetic interaction, geometric fragments, gravitational anomalies, and biochemical patterns. Each category revealed data that could be studied independently, but when combined, they formed a collection of features that did not fully match the behavior of known natural bodies. The question of origin remained open. If 3IATLAS followed a looping route through the solar system, then it might have observed these environments before. If it carried organic structures shaped by universal chemistry, then those structures might have existed long before Earth formed. Scientists did not frame this as a single discovery with one conclusion. Instead, they treated it as a collection of phenomena that needed deeper analysis. The possibility that the object had visited the system in earlier eras raised questions about the scale and time span of its path. A looping trajectory could reflect gravitational interactions across long periods. It might also indicate that the object passed through regions of interest in a predictable cycle. Whether these cycles aligned with planetary development or changes in biological environments remained unknown. Researchers approached this topic with caution, noting that coincidence and correlation must be evaluated carefully. The data concerning organic residues added another layer of complexity. If the structures were capable of adapting across environments, they could be part of a broader pattern of how molecular systems form in space. These systems might reflect a type of chemistry that occurs naturally in environments rich in radiation and simple elements. The presence of such material did not confirm that the object carried life. It only suggested that the chemical traces were organized enough to warrant further study. As the teams continued to analyze the combined evidence, they focused on maintaining clear boundaries between what was known and what remained uncertain. The object's movement, the magnetic signals, the geometric properties of the fragment, and the organic patterns were all real measurements, but the meaning behind them was still unclear. Scientists emphasized that understanding would require more data, better models, and continued tracking as the object moved deeper into the solar system. By this point in the investigation, 3IATLAS could no longer be viewed as a simple interstellar body passing by chance through the solar system. Its trajectory pointed toward important environments, its emissions showed repeating structure, and its residue contained molecular signals that resembled early biochemical patterns. For many researchers, these findings opened new lines of inquiry about how objects interact with planetary systems and how chemistry behaves in deep space. If the object had been to this system before, then its earlier passages might hold clues to changes in planetary surfaces or magnetic fields. The broader implications of these possibilities extended beyond astrophysics. They touched on questions about how life might form across different environments and how early chemical systems evolve. They also raised questions about what kinds of objects could travel across star systems and maintain stability over long periods. Scientists did not present these ideas as answers. They presented them as areas in need of careful and continued study. With the current data, the object appeared to be more than a visitor moving through the solar system once. Instead, it might reflect a pattern that repeats at long intervals. If this interpretation was correct, 3IATLAS could be part of a cycle that aligns with developments on planetary surfaces or changes in environmental conditions. The precise reason for its return remained unknown. But if the object had passed near the system before and was returning now, this encounter was not isolated. Taken together, the observations formed a picture of an object whose presence may be connected to long-term cycles in the solar system. Whether those cycles involved geological processes, environmental shifts, or something more fundamental was still unclear. Researchers proceeded with caution, knowing that the interpretations must be guided by evidence and not assumptions. But the possibility that 3IATLAS had moved through this region before and was doing so again suggested that this was more than a single event playing out in isolation. If that was the case, then this was not simply an object passing through space. It could represent a repeating presence, possibly observing cycles of planetary development, human progress, or maybe something much deeper encoded in Earth's own timeline.